All right, just some announcements. One of the things, there's actually a worksheet on capacitors on Canvas. It's not a long worksheet. It just to get you to understand the relationship between the electric field and the potential in a parallel plate capacitor when you have a dielectric in it and when you don't. Or when you have a conductor in between the plates and you don't. So I had this capacitor worksheet, and this is going to be due next Wednesday. So today is the 29th. So what's next Wednesday? Hold on a second. The 6th? Okay, so it's due next Wednesday, the 6th. Everyone clear on that? The capacitor worksheet that's on Canvas. So this worksheet is on Canvas, and it's due on the 6th. Okay, and then homework 4 is due tomorrow evening. I will have the 210R class today, so I will be answering questions on that today. And of course, I'll put the video for that presentation, for that class, as soon as I can, so that those of you who are not in 210R can actually maybe use that to help guide you through the homework. Don't forget, there's always tutoring from 12:30 to 4:30. Okay. Do you folks have any questions before I get started? Okay, so I wanted to do a couple of demos actually. So let me change my view here. What I have is this Wimhurst generator. And actually, I don't want to bring this, actually I shouldn't be bringing this too close. Actually, let me move it the other direction. I don't want to bring it too close to my computer. Let me bring everything back so you can see it. Okay, so what I have here, and I'll show it to you guys, is a board, a PC board. And the PC board...
Hey, Professor Calabresi, we're not able to see anything. The screen's on your speaking screen only.
Oh, I'm sorry. I think I forgot to change something. Thank you for... reminding me. Okay, sorry about that. Okay, so I have this printed circuit board, and it has gaps in it. I don't know if you can see the gaps in the printed circuit board. So what I'm going to do is I'm going to use this Wimhurst generator, and I'm going to apply a large voltage between the ends of this printed circuit board. And maybe let me dim the lights a little bit. Okay. So I showed you the Wimhurst. I've shown you the Wimhurst before. Okay, so here we go. It's really more of a proper to charge demo, but it's a fun demo. Okay, so what I'm doing is I'm charging up the the Wimhurst generator to a large enough voltage so that in between the little gaps, the electric field is very high and the dielectric breaks down. And you see that spark. Okay, so were you guys able to see that spark? Yes, no? Okay, good. All right, so let me do one more little demo. This next one's not as safe. Okay, let me turn the lights on a little bit. This has to do with dielectrics and capacitors. So I have, they call it a dissectable jar. It's basically, it's a capacitor basically, because I have two conductors and I'm going to put a dielectric in between them. I got to be careful how hard I push this in because otherwise I can't take it apart. And what I'm going to do is I'm going to charge this capacitor up. So let me charge this up. Uh-oh. Hold on a second. I hear something arcing. Okay, we'll try one more time. So I'm charging about my capacitor. And I'm going to disconnect it. That's one. And let me do it one more time. Sorry. I got to charge it up again. I messed up my demo. Let me charge it one more time. I just got shocked there, by the way. Okay. Let's try it one more time. So I'm charging this up. I will disconnect the capacitor. Okay. All right, so I'm actually going to short the capacitor. I don't know if you'll see it. I don't know if you heard a tick mark, a little tick on it. So I'm going to take this apart. And there's Walter Lewin, he does the MIT lectures, he does his demo. He takes it apart, then he puts it back together again. And what he does, and I don't know if I can get this to work. He takes this device and he shorts the capacitor again. That didn't work very well. Darn. So I apologize, it didn't work very well. When I did it earlier, it worked fine. Sorry about that. So what should have happened, I will tell you what should have happened. I can charge this up with this Wimhurst. Then I can discharge it like I did, and when I put it back together again, it acts like it's charged up again. And the reason why it behaves that way when I discharge it and then put it back, take it apart and put it back together again, is because the dielectric itself will actually hold the charge. Okay, so I think what I'll try to do is I'll try to video this and then give you the guys the video so you can take a look at it. Okay, that way I don't waste time in class trying to get this to work. So I apologize for screwing that up. Okay. So let me just continue on our lecture involving dielectrics. The other day we talked about what happens when you place a dielectric in a capacitor. And we showed, well, we didn't show, but we talked about experimentally what happens is that the capacitance increases by a factor kappa. And kappa is called the dielectric constant of material. So when you have a parallel plate capacitor, you charge it up, you disconnect it, you insert a dielectric in the media, in between the plates. Now the capacitance of that thing has increased by a factor of kappa. And we're gonna, and this relationship is linear, and we're really focusing on materials in which the relationship is linear in this course. So we talked a little bit about the energy, what happens when you actually insert the dielectric in the capacitor, and we noticed that the energy stored decreases. So I want to do another example. Now, I'm not going to do the full example here. I created a video the other day and put it on YouTube in which I actually go through the entire example in gory details. I just kind of want to set it up and talk about the physics behind it, and then you can watch the video where I go through and describe everything about this particular problem. So suppose we have a capacitor. We charge it up to a total charge Q sub T, or Q naught, I guess we'll write Q naught. We remove the battery, and then we insert a dielectric such that it takes up half the volume between the plates. And of course, this has dielectric constant kappa greater than 1. So I guess the question is, what's the new capacitance of this system? What happens to the charge on the plates? We can also ask about the energy stored in the capacitor. And what's the potential difference? What's the potential difference between the plates? So we can ask a bunch of questions. We can also ask about the charge density. What happens? Okay. Since this thing was disconnected from the battery, the initial charge that was on the plates can't go anywhere, so the total charge stays the same. But what happens when I insert the dielectric in between the plates? Well, the charge is going to redistribute itself. So let's make the top one plus and the bottom one minus in terms of charge. The charge will redistribute itself so that on the left-hand side, the amount of charge on the left-hand side is going to be different than the amount of charge on the right-hand side. The charge density will be different on the left and the right. And so, but the total charge stays the same. So I can say that Q naught is equal to Q left plus Q right. Because the charge density has changed. And I would say sigma on the left is not equal to sigma on the right. And it's not equal to sigma naught, the original charge density. Okay. So we can say original charge density so that means, what does that say about the electric field here and here? What does it say about the electric field on the left and on the right? Well, on the left, E left is the electric field's got to be equal to sigma left over kappa epsilon naught. The electric field on the right has to be equal to sigma right over epsilon naught because there's no dielectric here. Now, how are these related to each other? That's the question. So I want to consider equal potentials in between the plates. So we know the field is going to be uniform. We're assuming the plates are large compared to their plate separation. So I want to consider an equal potential here at some value V. Whatever that value is, you can say it's 1 volt. So all along that blue dotted line is at 1 volt. What happens when you reach this boundary? Oops, sorry. I forgot to change my... Is that better? So what happens when you reach the boundary? You march across here, the potential is 1 volt, you hit the boundary. What must be true when you reach the boundary? The potential has to be continuous. So if the equal potential is 1 volt all the way across here, it must be all the way the same value all the way across here. If the potential is 5 volts here, along that dotted line, then it must be 5 volts all along this dotted line. It can't change at the boundary because otherwise you have an infinite electric field. It's not physical. So that means that the delta V on the left and the delta V on the right have to be the same. Well, if that's the case, and the plate separation here and here are the same, how do these two compare? E left equals E right. If the delta V's are the same, the E's on the left and the E on the right has to be the same. And in the video that I put on YouTube, and if I remember correctly, I sent you a link, I actually go through and show this. But in order to show this, I have to calculate sigma left and sigma right. So, how is this capacitor behaving? How can I treat this capacitor so that I can find the total capacitance of the system? I have 2 capacitors, basically, and the potential difference across them is the same. Aren't they in parallel? Aren't the capacitors connected in parallel? So this is behaving as if I have 2 capacitors in parallel. which means that C total is equal to C left plus C right. And so all I got to do is write an expression for C left and C right. Well, on the left-hand side, I have epsilon, I have kappa, epsilon naught. And then what's my area? Well, area, it's half the area of the plate. So if A is the area of a plate, then this is going to be half the area. Divided by D. And for the right-hand side, and then I sum them together. And if I know C sub t, and I know that this is Q naught, then delta V is going to be, for the whole thing, the potential difference between the two has to be Q naught over C total. So delta V, which is equal to delta V on the left and equal to delta V on the right, has to be equal to this ratio. Okay, so delta V is equal to Q naught, my original charge, because that's the total charge I have in the plates, divided by the capacitance. And then from that point on, I can figure out the total charge on the left. I can figure out the total charge on the right. I can figure out the charge density on the left, the charge density on the right, the electric field on the left, and the electric field on the right. So that's what I did in the video. And I don't want to take the time out here to go through all those details. Does anybody have questions on this? Oh, question is, how do I know they're in parallel? Well, what I've established the fact is that the delta V's are the same. When two elements are connected in parallel, isn't it true that the potential difference is the same? All right, if I have two capacitors in parallel, and let me erase my objectives for today's lecture here. If I have two capacitors in parallel, isn't the equivalent capacitance just C1 plus C2? Don't they both have the same potential difference across them? The same thing here. I have two that are in parallel. I'm not sure I understand what you mean. The series case would look like this. Let me put the dielectric in between the plates. That's a series case. Capacitors don't have the same potential in series, right? You're just talking about if they're exactly the same capacitor? I'm not sure I understand your question. Yeah, if the capacitors are identical, if the capacitors are identical, they will have the same potential across them. However, in this case, the potential across them is the potential across the power supply. If they were in series and you had identical capacitors, each capacitor would have half the power supply voltage. Capacitors add inversely in series, yes.
But how can we know just by the potential are same?
I'm sorry?
I mean, then how can we know just by those two potential are same? Then we can see
These two?
Yeah.
Well, okay, so let me go back through the argument. The blue dotted line is the equal potential, correct?
Yeah.
This is a line, and the reason why it's a straight line is because we know the electric field is constant. If I cross the boundary, I have to have the potential be the same value. Otherwise, at the boundary, I have a discontinuity, and the electric field is infinite. So that means the electric field, the electric potential all the way across this blue line has to be the same, whatever that number is. If I choose another equal potential line down here, the V is the same all the way across. I got to do that from the top plate to the bottom plate. That means the delta V between the top and the bottom plate on the right-hand side and the delta V on the left-hand side, they have to be the same.
So these potential are same, I mean, equal to each other is in general. It's not for a specific situation.
It's just that they're equal to each other. It's all I've established. Right? All I'm saying is the delta V on the left-hand side is equal to the delta V on the right-hand side, just like when I have two capacitors in parallel.
So delta V of the left side is equals to the delta V of the right side, and this one is always come true.
For this, yeah, when it's in this orientation, when it's set up like this, yes.
Gotcha now. Thanks.
Whereas in this case, is different because the total delta V, and again, all you got to do is draw your equal potential lines. The total delta V between these two plates is the delta V across this dielectric plus the delta V across this dielectric. That's a series connection. Okay. And in this particular case, then does that make sense then for everybody? So in regard to your question, Justin, this is the case for the series. Okay, good, good. All right. Any other questions? And I like going through this example, and I created a video for this example because of the fact there's a lot of questions that come up in understanding this, and there's a lot of subtleties, but if you understand this, you kind of understand, you get a better understanding of capacitance and the relationship between the electric field and the charge on the plates on the capacitor, etc. Okay. Yeah, Ty, in series, the Q's are the same. So if you look at the Q across here and the Q across here, they have to be the same. The Q on this plate, the Q on this plate, and the Q at this boundary has to be the same. Okay. Now, in addition, in the video I provided, I actually do the last problem in your PowerPoint notes. I ask, as I slide this in, as I slide the dielectric in, hold on a second. As I slide the dielectric in, what's the force on it? Is Q still, okay, so let me look at this. Is still Q this, is Q the same without the battery? Well, if there's no battery, there's no Q, right? I mean, you're talking about hooking up something like this. If you do that, there's no charge on the plate. Are you talking about charging them and then removing the battery somehow? Okay. Well, they're still connected in series. Well, actually, if you remove the battery, what's going to happen if you, that's a good question. What happens if you remove the battery? So you take this out, and then you connect this end to this end. These are originally were oppositely charged. You end up getting no charge at all. I mean, you can think of it as a series connection, but if you disconnect the battery and you do this, you have no charge. Regarding the PowerPoint notes, I emailed them to you guys. Yeah, I emailed them last night. I emailed them last night for the next chapter. I've been emailing them the whole semester. Yeah, last night I did the Canvas email. I'm trying not to post them, and the reason why is because there's accessibility issues with the files. Okay? I implore you folks to check your emails regularly. So I've sent you folks emails with PowerPoint notes throughout the semester. I'm trying not to put them on Canvas just because of accessibility issues. Doing email and hosting. What do you mean by hosting, Patrick? Okay. No, there's a problem with uploading my PowerPoints to Canvas, which I don't want to get into the legal issues. There's legal issues I'm trying to avoid. You understand what I mean, Patrick? And I'm circumventing it by emailing it to you. Okay. All right. Okay, so I want to do one more example. Yeah, and I apologize that I'm not putting them on Canvas, but there's some legal issues I'm trying to deal with regarding putting them on Canvas when the course is online. Okay, and so that's why I'm emailing them to you. All right. I want to do one more example, and then really we're done with this chapter. Suppose we have a parallel plate capacitor. We charge it to Q0. The battery is removed, and then we insert a dielectric. So it takes up the whole volume. I want to calculate the energy stored in the capacitor and the force on the plates due to the field. And yeah, by the way, I'm sorry if I wasn't clear enough about the class notes. I was going to email them to you, okay, just because of the issues I have to deal with. Okay, so we have a parallel plate capacitor, and they place the dielectric. And I want to look at the energy stored in this thing. And, you know, obviously I can write My total energy stored is U equals 1/2 C delta V squared, right? I can write it like that, or Q squared over, I can write it like this. Where C, your capacitance, in this particular case, is going to be kappa, that's not a kappa, epsilon naught A over D. I also wrote it a different way the other day. I wrote it like this. I wrote it like that the other day too. Well, without the kappa. I did it for the case where there was no dielectric in between the plates. So I can write it this way, I can write it this way. And for the parallel plate, I can write it this way too. So let's look at it from this point of view. I want to lift the top plate upward, a certain distance dx. And the reason why I'm doing this is I want to figure out what is the force on the plate. All right? What is the force due to the field on the plate? What force is the field exerting on the plate? So what I want to do is calculate U at x plus dx, or let's do it this way. U at d plus dx minus U at d. So I want to lift the plate up a small distance dx. And I want to look at the change in potential energy. And that's going to be equal to the work done by the field, or minus the work done by the field. When I take the difference between these two, if I subtract these two, I'm going to get the following. This is a dx. This is my delta U. But really it's not a delta U because I moved this an infinitesimal amount. This is really a du. So I should probably call it du. I should call this du to be more precise because I've displaced it by an infinitesimal amount. And so du dx is 1/2 kappa epsilon naught E squared A. And if you remember from Physics 205, this is minus the force due to the field. So the force due to the field is minus 1/2 kappa epsilon naught E squared A. This is the force due to the field. It's minus. Remember, my displacement was upward. My force due to the field is downward. So it means that the force on the plate is downward. That means that the plate is being attracted to the dielectric, which makes sense because the plate below it's negatively charged. Here's an interesting question. What is the force per unit area on the plate? What is the force per unit area, also known as the pressure, which is the magnitude of F over A? That's also the energy density. Okay, it's also the energy. So this pressure that's on the top plate is due to the energy density. Okay. I'm sorry, it's not due to the energy, but it's related to the energy density. Questions? Okay. And that's, to me, it's an interesting problem. I do a lot of these kind of example capacitors because I think it helps to better understand everything you've learned so far this semester. All right. So I'm done with capacitors. We've already lectured on Ohm's law. I did it in the lab. So we're already done with chapters 26 and 27, believe it or not. And so what I'm going to do now is I'm going to start on chapter 28. And this is really the heart of circuit analysis, at least for this course. We're going to analyze circuits, series and parallel. And then we're going to look at more complicated circuits. Of course, when you take Engineering 17, you'll look at even more complicated circuits than what we'll look at here. So this serves as a good introduction to what you learn in Engineering 17. We're going to look at series and parallel circuits first. And we're going to look at DC circuits. What does direct current mean? Because I really haven't talked about that a lot. What is direct current? Anybody want to guess what direct current means? Or a characteristic? Yeah, it's one direction flow. It doesn't have to be constant. It's just one direction flow. Even if the current is not constant, but it flows in one direction, we call it direct current. Of course, in this chapter, the current, for most problems we're going to be doing, except when we get the RC circuits, the current will be constant. Okay, but really, direct current involves flow of charge in one direction. And we've already talked about Ohm's law. So we will be applying Ohm's law. Just give me a second here. So we'll apply Ohm's law. And there's two other laws I'll talk about that are very important in analyzing circuits that are a lot of times not talked about when you just do series and parallel circuits. Like if you learn this in a high school class, the overreaching law guiding these circuits is really not discussed. Okay, and really not discussed until you actually look at the more complicated circuits where you have something that's neither series nor parallel. So I'll mention the other laws too, which to me are very important. So let's consider two resistors that are connected in parallel. So as a reminder, let me write down, first of all, let me write down Ohm's law. I'm gonna write it down this way. But in reality, Ohm's law really is this relationship where J over E is a constant independent of the applied electric field. Of course, if you write it this way, delta V over I is a constant independent of the applied voltage. But this is the original way Ohm's law was written. Okay. And we have two resistors in series. Again, what's a resistor? A resistor is an element in a circuit that is used to limit current or provide a certain delta V for a circuit. What do resistors look like? Generally, a resistor, when you think of resistor, it's really a device that obeys Ohm's law. They come in different sizes and different shapes. And we'll talk about them in lab today. And I'll say a little bit more about them in lab because I'll show you a resistor. They can be this small. Okay, this is a very small resistor. You're going to be using this resistor in lab for your next lab. Okay. This is another type of resistor. Again, it's small. Okay. And that one's a variable resistor, and I'll talk about that in the lab today too. So there's different kind of resistors. They could be wire wound. They can be made out of carbon, and those resistors are generally devices that do obey Ohm's law, meaning that this delta V over I is a constant over a range of applied voltages. Okay. A device like a light bulb is, even though the resistance can be defined, it really doesn't obey Ohm's law because of the fact that delta V over I is not constant for any delta V. So a symbol for resistor is just a squiggly line. If you're not actually using a resistor, like one of these guys, these teeny weeny guys, okay. If you're talking about two things in series, like a refrigerator and light bulb, usually you call them a load. But what happens when I connect two resistors in series to a power supply? Can I replace those two with a single resistor such that I get the same current? So what do we know here? Well, charge only has one path here. So the current through R1 and the current through R2 has to be the same. The charge per unit time that goes through R1 and the charge per unit time that goes through R2 have to be the same. So that means I1 equals I2. And we'll call it I. And this is due to conservation of charge. And of course, if this is at 0 volts, and I'm just making up numbers, this is 3 volts. Let's say it's a 3-volt battery. This point in the circuit is going to be at 3 volts. This point in the circuit will be at 0 volts. And this thing will be at some in-between voltage, V sub I for in-between. If you take the potential difference, 3 minus V sub I plus V sub I minus 0, you're going to get delta V, which is 3 volts. So that says that delta V R1 plus delta V R2 has to be equal to the delta V of the battery. And this is a consequence of conservation of energy. So, having said this, then, I can use Ohm's law to write this guy. I can write I times R1 plus I times R2 equals delta V. Which I can write as I times R equivalent. Well, look, all you guys cancel. So that means R1 plus R2 equals R equivalent. So I can replace those two resistors with one equal to R1 plus R2, and it will give me the same current. That's how resistors in series add. Okay, so now you have to remember This relationships, the relationships for capacitors and resistors. Or I can write our equivalent. However you want to label it. Notice the difference in the relationships. Okay. And the reason why they're different is because Q is C delta V and I is delta V over R. Notice that here, this is the numerator, here, this is the denominator. That's why the relationships are flipped. So now, what if the resistors are connected in parallel? Then what? And I had this derivation in your notes. Oh yeah, by the way, regarding the class notes, I had to take screenshots of the equations and copy and paste over the actual equations you see on my screen, because of the fact that when I try to print them out as a PDF, the equations are invisible. Every time I change version of PowerPoint because Microsoft updates it, the equation editor acts weird. So I had to take pictures of your equation, and so if you actually printed out your PowerPoint notes, you're going to have a lot of slides that are completely black with some white, which are the equations, and that's because of the fact that I'm having issues with the PowerPoint every time I change editions. So one of the things I want you to notice as I go around this loop, remember what the loop is, just a closed path, that if I add the voltage drops, if I sum the delta V's in this loop, I get 0. In other words, I go from 0 to 3 volts. So if I sum clockwise, I go from 0 to 3. That's an increase in 3 volts. And then from here to here, or actually from here to here, plus from here to here, I get a drop of 3 volts. So this goes up 3, that goes down 3, so the sum is 0. That's always true in a loop. Okay, that's always true in a loop. So an overriding law in such circuits is the fact that the sum of the voltage drops in a loop is equal to 0. And that's a consequence of the fact that the electric field is conservative. That if you integrate the electric field around a closed path, you get 0, because the integral is independent of the path. This statement is called either Kirchhoff's loop rule, or Kirchhoff's voltage rule, or Kirchhoff's voltage law. I see all different names for it. This is one of the overriding laws when you're analyzing the circuit. And when you have a circuit that's neither series nor parallel, and you can't use these equations, you actually have to apply Kirchhoff's loop rule. And there's actually another one called the current rule. Is everyone clear on that? And it's pretty obvious that if I go around and sum voltage drops, that their sum is going to be 0. And if I want to write this, maybe I should write it more formally. Okay, if I write it more formally, the sum of the voltage drops in the loop is equal to 0. That's Kirchhoff's loop rule. And we're going to make use of this next time, not today. Now, what if we have 2 resistors in parallel? Okay, so I have 2 resistors in parallel. R1 and R2. Of course, what I want to do is replace these two with an equivalent resistor. Since these two are in parallel, okay, let's say this is 3 volts and this is 0 volts. This points at, let me use a different color. This points at 3 volts. This points at 3 volts. This points at 0 volts. All these are at 0 volts. So you can see right away that the voltage drop across each resistor is exactly the same. That's what it means to be in parallel. And it is equal to the battery voltage. They're in parallel. So that means that delta V1 equals delta V2. But what happens to the electrons when you get to this point? This is called a node. And what happens when they reach a node? They have to decide which way they want to go. I can go this way or I can go this way. I can go either direction. So now that the current has 2 paths, so it'll actually break into 2 parts. Here and here. I can call this I1 and this I2. But this total current, the sum of these two has to be equal to that, because the only place the current's going to go is either this path or this path. Nowhere else. So that the total current but then I can use Ohm's law and say, oh, I1 is just delta V over R1. By the way, I forgot to write that. We can write this as delta V plus delta V over R2. And of course, if I want to replace these two resistors with a single one, I can write this side as delta V over R total. And the V's cancel. Notice the difference in the relationships. They're flipped, and people a lot of times make mistakes. They mess them up, okay? So look at those two sets of equations. Again, I have this derivation in your notes. So for resistors in parallel, back one, they just add as reciprocals. But I want to look at what I wrote here. I want to look at something important here, that the current here splits up at a node. That's due to charge conservation. The fact that they split up at a node is due to charge conservation. Whatever comes in here has to be equal to whatever goes out at this node. Whatever enters a node has to equal to whatever leaves a node. Or a junction, whatever you want to call it. And this statement is called Kirchhoff's junction rule, or Kirchhoff's current rule, or Kirchhoff's current law. I see it's written a bunch of different ways. Basically, the sum of the currents my indices are going to be weird here. Entering a node, and you can say it this way, the sum of currents entering a node equals the sum of the currents leaving a node, or just the sum of the currents at a node equals 0. This law, and then the previous law, the loop rule, used together will allow you to solve any circuit. These two only allow you to solve certain types of circuits. Now, in Engineering 17, you will learn ways or tricks to make some of the more complicated problems a little bit easier. They're all based on Kirchhoff's laws, though. So in this course, if you encounter a complicated problem, we're going to be solving them by brute force methods. But when you take circuits, you'll learn some nice techniques to make the problems a little bit easier. So here's a review of series and parallel. These are the equations. These are the relevant equations that we have for now. And like I said, if we don't have a circuit that's neither series or parallel, then we have to use Kirchhoff's laws, and my next lecture will be based on this. Okay, so what I want to do is a demonstration. I want to ask questions. Let me look at this. Yeah, so the sum entering equals the sum leaving. So, Morgan, whatever goes in here has to be equal to whatever comes out. I mean, imagine water flowing through a pipe. All right? So imagine water flowing through a pipe. And you reach a T. Whatever comes in here has to be equal to whatever goes out there. So your indices are going to be this current, and this current. So you have to define a convention, okay? Whatever's going into a node is positive, whatever is leaving a node is negative. I'm not sure I understand. I'm sorry, Morgan, I'm not sure I understand your last question. Yes, current is a measure of charge flow. And there is charge flowing through the node per unit time. I'm not saying the current is zero. Well, okay, I understand what you're saying. So here's a point, right? We're looking at a total current passing through an area. And I made this too big. So isn't it true that whatever goes in here could take either of these two paths? Let me write it this way. If I call this I, and I call this I1, and I call this I2, you agree with me that I is equal to I1 plus I2. Do you agree with me with that? So what if I move this to the other side of the equation and I write I minus I1 minus I2? What is that equal to? Zero. So there you go. Right? So that's what that means, right? So your indices is all the currents that are going through this node. Okay, it's everything that's going through there. So this is going through it and then this is coming out. And so that's what that represents. That's why, I mean, I can write it as this summation, or I can say the sum of the currents entering a node equals the sum of the currents leaving a node. It's the same thing. All I'm doing is putting the terms on the other side of the equation. We okay with that then? Everybody? Okay. All right, good. So let me do my little example. It's like one of my favorite demos, although I'm doing this online, so we'll see how this goes. I have here hold on a second. I have a big board with bulbs in it. So let me rearrange things. Okay, so let me move this back. I have 3 bulbs, and they're connected in series. And let me turn on the lights too, just so that you can see better. Just give me a second. And I ask some questions. Don't hesitate to blurt something out. Three bulbs. The first one is a 25 watt bulb. The second one is a 60 watt bulb. And I couldn't find a 100 watt bulb, but this is a 200 watt bulb. Okay? I have a switch here. If I flip on the switch, which one's going to be brightest? 25 watts, 60 watts, 200 watts. Which one will be brightest? Anybody want to guess? Well, I don't want to say guess, but anybody want to answer that question? And this is plugged into the wall, so I'm putting 120 volts into my system. Which one's going to be brightest? Hold on a second. The first one. Anybody agree with that? Oh, good question. Does it depend on the resistance, not the watts? That's a good question. So I guess the question, Justin, is why would you say the first one? I guess I should turn it on, right? You guys ready? I'm gonna flip the switch. You were correct, it was the first one. No, this was 25 watts. This is 60 watts. This is 200 watts. In fact, you can even see the 200 watts. I don't know if you guys can see. The 60 watt bulb is actually kind of lit. Can you guys see that? But the one with the lowest wattage is brightest. Why? It has more resistance, right? This has the most resistance. Remember, we talked about power the other day. Power is delta V squared over R. And so they're all rated at 120 volts. The 25 watt bulb has the lowest power. It means the highest resistance. Now, they're in series, so how is the current going to be through them, each one of them? Isn't the current going to be the same through each one of them, since they're in series? And since they all have the same current, the one with the biggest resistance has the biggest voltage drop, which is this one. So, I always get this question. You guys haven't asked it yet, but I'm gonna bring it up. I will always get a student that says, "Well, why don't you put the big one first? Does the order matter? What do you think?" Does the order matter here? Should I actually try it? Yeah, the order doesn't matter. So let me put the big one first. Doesn't matter. So another question that might come up is, oh, The 200 watt bulb doesn't work. What's wrong with that, saying that? Yeah, none of them works. If I take this guy out, it's the same thing as if it was dead. None of them would have to work. None of them would work. I'd actually have to bypass it to get it to work. I'd have to short this point out to get it to work. Now, all right, now I'm going to put them in parallel. Uh-oh. Oh, I forgot I got a jumper that. Hold on a second. I forgot a couple of jumpers. Okay. I forgot my jumpers here. All right, now, can you tell which one's brightest? It's pretty damn bright, right? The 200 watt bulb is pretty bright. Okay. Yeah, you bring up a good question, a good comment, Justin. One of the reasons why we wire lighting in parallel, right? Imagine if everything in your house was wired in series. Imagine if your air conditioner was wired in series to the rest of your house. You think it'd work? No. The air conditioner would be useless. That's why everything's hooked up in parallel. You can see, right, that light bulb is pretty darn bright. So let me try something else here. Let me take out the short. For some reason, this thing isn't cooperating. Let me get a bunch of 25 watt bulbs here. Let me take this one because it has too. This one has too low of a resistance. Let me do the following. So I have three 25 watt bulbs in series. They're going to be equally bright. Well, not that bright, and the reason why is because they're each one of them is going to have 40 volts across it. Now, if I take this bulb and put it here, what's going to happen to this guy? Does it get brighter or dimmer? This is a 60 watt bulb. I'm going to put it in parallel with the 25 watt bulb. Seems like it didn't make a difference. That's strange. I hope I didn't mess this thing up. Hold on a second. Nothing's happening. That's strange. Give me a second. Let me see if I can find one more bulb. Okay. For some reason, nothing's happening. Why is nothing happening? Oh, I know why it's not working. Something got disconnected in the back. Okay, hold on a second, because I something got disconnected in the back. So those of you who said it's going to get dimmer, you're correct. So the back of my board got disconnected. Sorry about that. And I'm not going to connect it while it's live. All right. But you're right. It gets dimmer. Why does it get dimmer? Yeah, let me do it with the 60 watt bulb. Let me put the 60 watt bulb in and let me. In fact, it goes completely off, right? That's the 60 watt bulb and a 25 watt bulb in parallel. So now because these two resistors are in parallel, the combination of the two resistors is going to be smaller than either one. That's why this one goes off. Okay? So what happened was, this wire came loose. Okay, I didn't see that. That's why my demo wasn't working. And I'm not going to screw it in, like I said, I'm not going to screw it in while this thing's live. Okay, that would not be a good result. So yeah, you folks are right. Hold on a second. Maybe I can get it in. Nope. Okay, I'll leave it like that. So these two, because the resistance gets smaller, the voltage drop will get smaller. And in fact, don't the other two get brighter? The other two actually get brighter. That's because the equivalent resistance gets smaller. So when you have things in parallel, when you have two resistors in parallel, the overall resistance gets smaller than either one of the two. It's something to remember. Do you guys have any other questions regarding this demo? Do you want me to try anything? Yeah, that's a good, Patrick, that's a good comment regarding the current and the bulb. You guys want to see any other combinations? Because usually when I do this demo, a lot of people have misconceptions of how this thing should work. Okay. Let me move my equipment out of the way. All right. And we only have, we have no time actually. So I'm going to stop here. So my next thing would be to do an example of taking a circuit like this one. And I did this with the capacitors. Basically take this circuit and break it down and analyze it. Calculate the equivalent resistance of the circuit, the total current in the circuit, all the voltages across all the resistors, and also the power or the energy dissipated by all the resistors, because the resistors will use up energy. So I think what I'll do is I'll do this example on Monday, because the lab will probably take me most of the time today to discuss. So I'll see you folks in about 20 minutes, okay?